What if I told you that a simple experiment with light performed over 200 years ago challenged everything we thought we knew about the nature of the universe? Quite a bold claim, isn't it? But that's precisely what the double slit experiment did. Let's take a step back to the early 19th century. In the year 1801, a British polymath named Thomas Young decided to play with light. Young was a curious man, a scientist who dabbled in various fields, but he is best remembered today for his double slit experiment. Imagine a barrier with two slits and a light source behind it. When the light passes through the slits, it forms a pattern on a screen placed behind the barrier. Now, if light were made up of particles, we would expect to see two bright lines on the screen, one for each slit. But Young's experiment didn't show that. Instead, it revealed a series of bright and dark bands, a pattern that only waves would create. This was a direct challenge to the particle theory of light. The pattern observed was characteristic of waves, not particles. It was as if the light waves passing through the slits were interfering with each other. In some places, they would crest together, creating bright bands. In others, they would cancel each other out, forming dark bands. Over the years, the double slit experiment has been repeated countless times with consistent results. It's one of the most compelling pieces of evidence that light behaves like a wave. Moreover, it's not just light. The same experiment has been carried out with other particles like electrons and neutrons, further deepening our understanding of the quantum nature of matter. So, what started as a simple experiment with light has had profound implications, fundamentally altering our understanding of the universe. It's a testament to the power of curiosity and the pursuit of knowledge. Stay tuned as we unravel the fascinating tale of the double slit experiment, a simple setup with profound implications. Imagine a barrier with two slits, a light source behind it, and a screen at the back. Sounds simple, doesn't it? Now, let's delve a little deeper into this setup. Picture a room dimly lit with a single light source. This light source could be a laser or any source of monochromatic light, which means light of a single wavelength. This light source is positioned in such a way that it directly faces a barrier, an opaque wall of sorts. Now, this isn't just any ordinary wall. It's a unique one with two very narrow slits cut into it. These slits are so thin that only a tiny fraction of light from our source can pass through them. Now, imagine behind this barrier, at a certain distance, there is a screen. This screen is our observation point, a canvas waiting to capture and display the behavior of light after it interacts with the barrier and its slits. Let's take a moment here. If we were to consider light as mere particles, similar to bullets from a gun, we would expect a specific pattern on the screen. The light particles passing through the left slit should create a bright line on the left side of the screen, and those passing through the right slit should create a bright line on the right side of the screen. Essentially, we'd anticipate two bright lines, each corresponding to one slit. This setup, as complex as it might sound, is remarkably simple in its construction. It's a testament to the brilliance of Thomas Young, who first performed this experiment in the early 19th century. It's a setup that's been replicated countless times, each time throwing more light on the fascinating nature of, well, light itself. One might expect to see two bright lines on the screen, right? But what we see is far more intriguing. So what do we witness on the screen? Well, brace yourself for a surprise as we step into the world of wave interference and quantum mechanics in the next segment. Instead of two bright lines, we observe a series of alternating light and dark bands on the screen. But why? This phenomenon, contrary to what we'd expect if light were simply particles, is a result of what is known as wave interference. Let's break that down. When you drop two pebbles into a pond at different points, they each create ripples. These ripples spread out, and eventually they intersect. Where the crests or troughs of these waves coincide, they reinforce each other, creating a stronger wave. This is called constructive interference, and it results in the bright bands we see on the screen in the double slit experiment. On the other hand, where a crest from one wave meets a trough from another, they cancel each other out. This is destructive interference, leading to the dark bands in the pattern. So, the alternating light and dark bands we see in the double-slit experiment are a direct result of these two types of interference happening concurrently. Now let's return to the double-slit experiment. As the light passes through the two slits, it behaves like waves in a pond, creating an interference pattern on the screen behind the barrier. The crests and troughs of the light waves interfere with each other, just like the ripples in the pond. This results in a pattern of bright and dark bands, corresponding to areas of constructive and destructive interference respectively. This pattern, puzzling at first, is the telltale sign of wave behavior. It's a departure from the simple particle model of light, which would predict only two bright lines corresponding to the two slits. This surprising outcome prompts us to reconsider our understanding of light. It's fascinating, isn't it? How something as ubiquitous as light can still hold such mysteries, and how a simple experiment can lead us to question and refine our understanding of the fundamental nature of the universe. This pattern, characteristic of waves, was the first indication that light was not just made of particles. The double-slit experiment didn't just stop at light. It opened a Pandora's box of quantum enigmas. As our knowledge expanded, so did our curiosity. The wave-particle duality of light was a groundbreaking discovery. But the question arose, is light alone in this dual nature, or do other particles exhibit this behavior as well? The answer, as it turns out, is a resounding yes. To explore this, scientists turned to electrons and neutrons, the building blocks of the very universe. Similar to the experiment with light, they fired these particles at a barrier with two slits, and what happened next was nothing short of extraordinary. Just like light, these particles didn't create two distinct lines on the screen as one might expect. Instead, they formed an interference pattern, much like waves. Even when sent through one at a time, these particles somehow knew to form a pattern, as if they were interfering with themselves. This was a clear indication that electrons and neutrons, much like light, also exhibit wave-like behavior. But here's where it gets even more puzzling. If we try to observe which slit the particle goes through, the interference pattern disappears and we are left with two distinct lines. This phenomenon, known as the observer effect, essentially means that the act of observation changes the outcome. It is one of the most baffling aspects of quantum mechanics, and it all stems from the humble double-slit experiment. In the world of the very small, the rules of the game are quite different from what we're used to. Particles can be in multiple places at once. They can behave like waves, and they can even change their behavior when observed. These quantum puzzles, though perplexing, offer a fascinating glimpse into the inner workings of the universe. This experiment, simple in its design, became a cornerstone in our understanding of quantum mechanics. The double-slit experiment, a bedrock of modern physics, forces us to rethink our understanding of the universe. This seemingly simple experiment, first carried out by Thomas Young in the year 1801, has had far-reaching implications. It has compelled us to unlearn and relearn our perceptions of light and matter. The experiment, as simple as shining light through two slits onto a screen, revealed a pattern of bright and dark bands. This was not what we expected if light were merely particles. Instead, the pattern bore the hallmark of wave interference, causing us to reevaluate our understanding of light as a wave. This revelation, however, was just the beginning. The double-slit experiment didn't just stop at light. It was repeated with other particles, like electrons and neutrons, and lo and behold, they too exhibited wave-like behavior. This experiment, therefore, served as a gateway into understanding the quantum nature of matter, a concept that is still perplexing and intriguing to many of us. The double-slit experiment is much more than an experiment. It's a testament to human curiosity and our quest to understand the universe. It has repeatedly challenged our notions, prompting us to dig deeper, question more, and seek answers that often lead to more questions. It's a testament to the fact that our understanding of the universe is ever evolving, constantly reshaped by new discoveries and insights. The conclusions drawn from the double-slit experiment have had profound implications in fields far beyond physics. They have influenced the development of technologies that we use every day, from lasers and microscopes to quantum computers and even the internet. Next time you switch on a light, remember the double-slit experiment and the mind-boggling mysteries it uncovers about our universe. Don't forget to like, share, and subscribe for more fascinating science stories. And as always, keep your curiosity alive.